Swayam Prabha. Digital India. Educated India.
Dear all, in continuation of the fundamental concept of random variable and random experiment, further we are going to discuss some problem in probability, and sometimes we have to recollect the basic ideas so that you can easily understand how to solve the problem of probability in random variable and random experiment. Now, once again we recollect that finite probability. An experiment is a procedure that yields one of a given set of possible outcomes. The sample space of the experiment is the set of possible outcomes, and the event is a subset of the sample space. By Laplace, the definition, the probability of an event with finitely many possible outcomes will now be stated. Let us start with the further definition of probability, that if S is a finite non-empty space of equally likely outcomes and E is an event that is a subset of S, then the probability of E is P of E equal to number of possibilities is E by total number of outcomes is S. According to Laplace definition, the probability of event is between 0 and 1, and note that if E is an event from a finite sample space S, then the E lies between 0 to S, because E is a subset of S. E is a possible number and S is a total number of possible outcomes. Therefore, E is always subset of S. Thus, 0 less than or equal to P of E, which is equal to cardinality of E by cardinality of S, which is less than or equal to 1. So, this is the makeable note to understand the probability of an event. Now, we will go to discuss some more examples. Let us start with example 1. An urn contains 4 blue balls and 5 red balls. Urn contains blue balls and red balls, respectively 4 and 5. What is the probability that a ball chosen at random from the urn is blue? So, we have to understand the total number of outcomes and number of possibilities of getting a urn from blue. That is most important. So, that to calculate the probability, note that there are 9 possible outcomes and 4 of these possible outcomes produce a blue ball. Hence, the probability that a blue ball is chosen is 4 by 9. So, this way we can calculate the values of getting a probability that ball chosen random from the urn is blue. Now, we are going to discuss another example, that is, what is the probability that when 2 dice are rolled, the sum of the numbers on the 2 dice is 7. There are total of 36 equally likely possible outcomes, because 2 dice are rolled. One phase consists of 6, another phase consists of 6, totally 6 into 6 is 36 of 2 dice are rolled. Therefore, the product rule can be see this, because each dice having 6 possible outcomes. Therefore, the total number of outcomes when 2 dice are rolled is 6 into 6 is 6 square is 36. There are 6 successful outcomes, namely 1 6, 2 5, 3 4, 4 3, 5 2 and 6 1 are the successful outcomes, where the values of the first and the second dice are represented by an ordered pair. Hence, the probability of 7 comes up when 2 fair dice are rolled is 6 by 36 equal to 1 by 6. Further, some more example. In a lottery, players win a large prize when they pick 4 digits that match in the correct order. 4 digits selected by a random mechanical process. The smaller prize is 1 if only 3 digits are matched. What is the probability that a player wins large prize? What is the probability that a player wins a small size? Okay. So, this is a question. Now, the solution is, there is only one way to choose all 4 digits correctly. By the product rule, there are 10 power 4 equal to 10,000 ways to choose the 4 digits. Hence, the probability that a player wins the large prize is 1 by 10,000 equal to 0.0001. Now, further analysis, player wins the smaller prize when they correctly choose exactly 3 of the 4 digits. Exactly 1 digit must be wrong to get 3 digits correct, but not all 4 correct. By the sum rule, to find the number of ways to choose exactly 3 digits correctly, we add the number of ways to choose 4 digit matching the digits picked in all but ith position for I equal to 1, 2, 3, 4. To count the number of success, if the first digit is incorrect, there are 9 possible choices for the first digit, all but the one correct digit, and one choice for each of the other digits, namely the correct digits for these slots. Hence, there are 9 ways to choose the 4 digits where the first digit is incorrect, but the last 3 are correct. Similarly, there are 9 ways to choose the 4 digits where the second digit is incorrect, 9 with the 3 digits is incorrect, and 9 with the 4th digit is incorrect. Hence, there is a total of 36 ways to choose the 4 digits with exactly 3 of the 4 digits correct. So, the probability that the player wins a smaller prize is 36 by 10,000, which implies 29, which implies 9 by 2,500, which is equal to 0.0036. So, this way we can calculate that players win the large prize and players win the small prize. I hope you can understand the problem related to basic probability ideas. Next example, there are many lotteries now that award enormous prizes to people who correctly choose a set of 6 numbers out of first n positive integers, where n is usually between 30 and 60. What is the probability that a person picks the correct 6 numbers out of 40? So, here we have to use the combination. there is only one winning combination. The total number of ways to choose 6 numbers out of 40 is 40C6 equal to 40 factorial by 40 minus 6, 34 factorial into 6 factorial, which is equal to 3838380. Consequently, the probability of picking a winning combination is 1 by the outcomes, which is equal to 0.00000026. So, here these symbols denotes the approximate the values of the chances of getting the persons picks the correct 6 numbers out of 40. Next example, find the probability that a hand of 5 cards in poker contains 4 cards of one kind. How to calculate the probability? By the product rule, the number of hands of 5 cards with 4 cards of one kind is the product of the number of ways to pick one kind, the number of ways to pick the 4 of this kind out of 4 in the deck of this kind, and the number of ways to pick the 5th card like that. Now, the combination is 13C1 and 4C4 and 48C1, and then product them. So, there are 52C5 different hands of 5 cards. Therefore, the probability of hand contains 4 cards of one kind is 13C1 into 4C4 into 48C1 divided by total number of outcome is 52C5. Therefore, the resultant is 13 into 1 into 48 divided by 2598960, which is equal to approximately 0.00024. So, this way we can hand a 5 cards in poker contains 4 cards of one kind. So, this is the value of the probability. Next example, what is the probability that a poker hand contains a full house, that is 3 of one kind and 2 of another kind? By applying the product rule, the number of hands containing full house is the product of the number of ways to pick 2 kinds in order. So, the number of ways to pick 3 out of 4 for the first kind, the number of ways to pick the 2 out of 4 for the second kind, like that. The order of the 2 kinds matters because, for instance, 3 queens and 2 aces is different from 3 aces and 2 queens. Therefore, the number of hands containing full house is 13C2 into 4C3 into 4C2. So, that the resultant will be 3744, because there are 52C5 equal to 2598960 poker hands. The probability of full house is 3744 divided by 2598960. It is approximately equal to 0.0014. Next example, what is the probability that the numbers 11, 4, 17, 39 and 23 are drawn in that order from a bin containing 50 balls labeled with the numbers 1 to 50 if A, the ball selected is not returned to the bin, before the next ball is selected, but 2 the ball selected is returned to the bin before the next ball is selected. Here we have a probability of the numbers are 11, 4, 17, 39 and 23, and the bin contains 50 balls. Now we have 2 questions. The ball selected is not returned to the bin before the next ball is selected. So this is the probability comes that the sampling without replacement. So first we have to apply the product rule of the 5 balls, that is 50, 49, 48, 47, 46 is 254, 251, 200 ways to select the balls, because each time the ball is drawn there is one fewer ball to choose from. Consequently, the probability that 11, 4, 17, 39 and 23 are drawn in that order is 1 by total number of outcomes. This is an example of sampling without replacement. Another subdivision B states that the ball selected is returned to the bin before the next ball is selected. Therefore, every time if you select the ball, you have to return and then replacement is possible. Therefore, there are 50 power 5, which is equal to 3, 1, 2, 500, 000 ways to select the balls, because there are 50 possible balls to choose from each time a ball is drawn. Consequently, the probability that 11, 4, 17, 39 and 23 are drawn in that order is 1 by 312, 500, 00. So this is an example of sampling with replacement. Next idea is probabilities of complements and union of evens. So already we come across the theorem, once again recollect it. Let E be an even in a sample space S. The probability of even E bar equal to S minus E. Then the complementary event of E is given by P of E complement equal to 1 minus P of E. So the proof is E complement is S minus E. Therefore, cardinality of E complement is equal to cardinality of S minus cardinality of E. Therefore, probability of E complement is cardinality of S minus cardinality of E by S, which is equal to S by S 1 minus E by S, which is equal to 1 minus probability of E. So this way we can understand the complement of one event to the another, and combined together is a union of events. Now we have a theorem of union of 2 events, like E and E2 be the events in a sample space. Then probability of E1 union E2 is equal to probability of E1 plus probability of E2 minus probability of E intersection E2. Now using this formula in the section, for the number of elements in the 2 of the sets follows that simply the cardinality of E1 and E2 union them, so that the cardinality of E1 plus cardinality of E2 minus cardinality of E1 intersection E2. Then you take a probability. So probability of E1 union E2 is nothing but cardinality of E1 union E2 by total number of space, and you know the formula, then apply here. Cardinality of E1 union E2 is cardinality of E1 plus E2 minus E1 intersection E2 divided by sample space, which is equal to cardinality of E1 by S and cardinality of E2 by S, then cardinality of E1 intersection E2 by total space, sample space, then this is probability of E1, probability of E2 and probability of E1 intersection E2. Now, we have to understand the meaning of conditional probability. So, let us start with some understanding of basic idea, so that you can easily understand the conditional probability. Suppose that we flip a coin 3 times and all 8 possibilities are equally likely. Moreover, we know that the event F, that the first flip comes up tails occurs. Given this information, what is the probability of the event E? That an odd number of tail appears. Because the first flip comes up tails, there are only 4 possible outcomes, that is TTT, TTTH, THT and THH, where H and T represent heads and tails respectively. An odd number of tails appears only for the outcomes of TTT and THS, because the 8 outcomes have equal probability. Each of the 4 possible outcomes, given that F occurs, should also have an equal probability of 1 by 4. This suggests that we should assign the probability of 2 by 4 equal to 1 by 2 or E. So, this 2 by 4 is 1 by 2 to E, given that F occurs. So, this probability is called as conditional probability of E given F. So, this way we have to start that conditional probability. That is, the definition says that if E and F are the events and the probability of F is always positive, then the conditional probability of E given F is denoted by probability of E by F, is defined as probability of E by F is equal to probability of E given by F is denoted by probability of E intersection F by probability of F. So, this way we can define the conditional probability. Now, based on this, we have a problem. A bit string of length 4 is generated at random, so that each of the 16 bit strings of length 4 is equally likely. Then what is the probability that it contains at least 2 consecutive zeros, given that its first bit is a 0? Assume that 0 bits and 1 bits are equally likely. Now, the solution is, let E be the event, that a bit string of length 4 contains at least 2 consecutive zeros. Let F be the event, the first bit of a bit string of length 4 is 0. Therefore, the probability that string of length 4 has at least 2 consecutive zeros, given that its first bit is 0, which equals probability of E given by F is equal to probability of E intersection F by probability of F, that is the requirement. Next, we will go to the example. What is the conditional probability that a family of 2 children has 2 boys, given they have at least 1 boy? Assume that each of the possibilities BB, BG, GB and GG is equally likely, where B represent boys, G represent girl. Note that BG represent a family with an older boy and a younger girl, while GB represent the family with older girl and younger boy. So, this way we design the BG and GB, so that how to calculate 2 children has 2 boys, given they have at least 1 boy. So, what is the probability? The solution is, let E be the even. The family with the 2 children has 2 boys. Let F be the even. The family with the 2 children has at least 1 boy. It follows that E equal to BB and F is equal to BB, BG, GB, and E intersection F equal to BB, because the 4 possibilities are equally likely. It follows that probability of F equal to 3 by 4, probability of E intersection F equal to 1 by 4. Now, we conclude that probability of E by F equal to probability of E intersection F by probability of F is equal to 1 by 4 by 3 by 4, which is equal to 1 by 3. So, this way we can understand the conditional probability. Next, we have to discuss the independence. Suppose a coin is flipped 3 times, as described in the introduction to our discussion of conditional probability. Thus, knowing that the first flip comes up tails, after the probability that tails comes up an odd number of times. In other words, is it the case that probability of E over F equal to P of E? This equality is valid for the even E and F, because E over F, probability of E over F equal to 1 by 2 and probability of E equal to 1 by 2, because this equality holds. We say that E and F are independent events. When 2 events are independent, the occurrence of one event given no information about the probability that the other event occurs, because probability of E over F is equal to probability of E intersection F divided by probability of F. So, asking whether probability of E over F equal to probability of E is the same as asking whether probability of E intersection F equal to probability of E into probability of F. So, this leads to the definition. So, the definition is the events E and F are independent if and only if probability of E intersection F equal to probability of E into probability of F. Another example of the independent is, suppose E is the event, that a randomly generated bit string of length 4 begins with 1 and F is the even that this bit string contains an even number of ones, or E and F independent if 16 bit string of length 4 are equally likely. So, what is the resultant of this? There are 8 bit strings of length 4 that begins with 1 followed with 3 zeros, 1001, 1010, 1011, 110, 1101, 1110 and 4 ones. So, these are all the 8 bit string of length 4 that begins with 1, and there are 8 bit string of length 4 that contain even number of coins, that is all are 0, 0 0 1 1, 0 1 0 1, 0 1 1 0 and 1 0 0 1, 1 0 1 0, 1 1 0 0 and 4 ones. Because there are 16 bit strings of length 4, it follows that probability of E equal to probability of F, which is equal to total number of possibilities divided by outcome is 8 by 16, which is equal to 1 by 2. The intersection of two event E and F is 4 ones, 1100, 1010, 1001. and the probability of this intersection of two event is probability of E intersection F equal to 4 by 16 equal to 1 by 4, because probability of E intersection F equal to 1 by 4, which is equal to 1 by 2 into 1 by 2 equal to probability of E into probability of F. Therefore, probability of E intersection F is equal to probability of E into probability of F. It means the two events E and F are independent. Next example, assume as in the example 4 that each of the 4 ways a family can have 2 children is equally likely, or the events E that the family with the 2 children has 2 boys, and F that a family with the 2 children has at least 1 boy is independent. Now, the solution to this problem is you take E, because E is 2 children is boys BB. So, we have probability of E equal to 1 by 4. In example 4, we showed that probability of F equal to 3 by 4, and that probability of E intersection F equal to 1 by 4. Therefore, because of independency, probability of E into probability of F equal to 1 by 4 into 3 by 4 equal to 3 by 16. Therefore, probability of E intersection F is 1 by 4 and probability of E into probability of F is 3 by 16. Therefore, they are not equal to one another, implies that E and F are not independent. So, this way we can do for not even independent. Another example are the events E that a family with 3 children has children of both sexes, and F that this family has at most 1 boy independent. Assume that the 8 ways a family can have 3 children are equally likely. Now, we have to find the solution to this problem with the help of the assumption each of the 8 ways a family can have 3 children. They are BBB, BBG, BGB, BGG, GBB, GBG, GGB and GGG has a probability of 1 by 8, because E is equal to what? BBG, BGB, BGG, BGBB, GBG, GGB. So, totally this, and F is has at most 1 boy. Therefore, BGG, GBG, GGB, GGG, and E intersection F is equal to BGG, GBG and GGB. So, 3 values only come. Therefore, probability of E equal to 6 by 8, which is equal to 3 by 4, and probability of F equal to 4 by 8 equal to 1 by 2, implies probability of E into probability of F is equal to 3 by 4 into 1 by 2, which is equal to probability of E intersection F, which is equal to 3 by 8. So, this way we can do or equally likely of 2 independent events. Next idea is pairwise and mutual independence. For example, the events E1, E2 and so on En are pairwise independent if and only if probability of Ei intersection Ej equal to probability of Ei into probability of Ej for all pairs of integer I and j with 1 less than or equal to I less than j less than or equal to n. So, these events are mutually independent if probability of Ei1 intersection Ei2 and so on intersection Eim equal to probability of Ei1 into probability of Ei2 and so on probability of Eim, where I comma I j comma j is equal to 1, 2, 3 and so on m, or integer with 1 less than or equal to I1 less than I2 and so on, less than Im less than or equal to n, and m is greater than or equal to 2 is what, pairwise integer of mutually independent events. Now, based on this, we have an example. A coin is biased, the probability of heads is 2 by 3. What is the probability that exactly 4 heads come up when the coin is flipped 7 times, assuming that the flips are independent? The solution are, there are 2 power 7 equal to 128 possible outcomes. When a coin flipped 7 times, the number of ways 4 of the 7 flips can be heads is 7C4, because the 7 flips are independent. The probability of these outcomes are 4 heads and 3 tails is 2 by 3 whole power 4 into 1 by 3 whole power 3. Consequently, 7C4 into 2 by 3 whole power 4 into 1 by 3 whole cube, which is equal to 35 into 16 by 3 power 7 equal to 560 by 2187. So, this way we can do for the pairwise of the probability and corresponding to independence, mutual independence. Next, already we discussed the Bernoulli trials and binomial distribution, and once again we recollect it. The probability of exactly k successes in n independent Bernoulli trials with the probability of success p and probability of failure is q equal to 1 minus p is nck into p power k into q power n minus k. Then the proof is, the n Bernoulli trials are carried out. The outcomes of n tuple can be written as T1, T2 and so on Tn, where Ti equal to S for success or Ti equal to F for the failure, for I equal to 1 to n, because the n trials are independent. So, the probability of outcomes of n trial consists of k success is n minus k, failure is p power k into q power n minus k, because there are nck k tuple of success and failure that contain exactly k ss. So, the probability of k success is nck into p power k into q power n minus k. Now, we have a problem related to Bernoulli trials and the probability binomial distribution, that suppose the probability that a 0 bit is generated is 0.9, that the probability that a 1 bit is generated is 0.1, and that bits are generated independently. What is the probability of exactly 0 bits are generated when 10 bits are generated? So, by theorem, the probability that exactly 0 bits are generated is B of probability of 8, 10, 0.9 is 10C8 into 0.9 whole power 8 into 0.1 the whole square. So, this binomial distribution B stands for this, and then the corresponding formula is this. Therefore, the resultant is 0.1937 and so on approximately comes. So, this is the examples of binomial distribution, and note that the sum of the probability that are k success when n independent Bernoulli trials are carried out for k equal to 0 to n, which equals to summation k running over 0 to n is nck into p power k into q power n minus k and this can be written as a binomial of success and failure addition the whole power n equal to n. So, this way we can do for binomial and Bernoulli equations.